The principle of a generator now works that in a similar way, but this time I'm going to start with my north and south. Okay, and this time the change in direction, or the not change in direction, the turning is caused by me. I cause the thing to turn, and because I'm causing this thing to turn, I'm moving. In this case, you can see here. Here's my field pattern, and at this point here, I am pushing it up. So if this is my magnetic field, I'm causing my wire to move perpendicular through a magnetic field, which means I am causing a current to flow in here. Now here goes my magnetic field. So as I'm pushing it up here, and I'm not exactly sure about the direction, because here we use the right hand rule to determine direction. Oh, I do that again. Here I use the right hand rule to determine direction. So in other words, if I wanted to now find out in what direction the current will be going, so let me do that. If I am pushing it up or rotating it up, again this is a loop. It loops like this. Okay, so this is just my wire. Okay, and I'm now viewing it from this side, but this wire is connected to, let's say, a little light. Okay, this is not good enough. Okay, here's my wire. Again, they connected to a split ring, and this split ring is connected to a little light. Okay, and if there's a current, the light will shine. Okay, now these are called bushes. That's what connects the split ring to the external circuit, and there's my loop. So if I'm pushing this thing up, let's see in what direction will the current flow. So this time I use my right hand rule. Okay, if I'm pushing it up, I'm and my palm is from north to south. Okay, then what I'm doing is the current is going to be flowing towards me. So this one will be flowing towards me, and that one will be flowing away from me. Okay, now you'll notice that at this point I'm at a 90-degree angle with my magnetic field line. But if I turn it now enough so that I'm here at the top, we said that the current that I'm inducing, it's called inducing a current, was flowing towards me. I'm pushing it to the top. This one is flowing away from me. But notice here at the top, when I'm my magnetic field now, that's now assuming that these are two equal sized magnets. At the top, it is moving in this direction, and my magnetic field is also in that direction. So now I'm moving my wire in the same direction as my magnetic field. Do you get that? And what Faraday found is it's only when you move it in a perpendicular direction that you're causing a current. So at this point here, I have zero current. I have my 0 ampere. Okay, so in other words, and now I go further. Now the moment I come to this side, notice what happens once I pass this side. My current is away from me. So on this side, let's say I had a current on this side that's bigger than 0. On this side I measured my current bigger than 0. On this side my current will be on that if this was an ammeter, if that was an ammeter, as it's going towards this, I might have a positive reading, but the moment I reach that top and I come down, I'll have a negative reading, because the moment I pass so again, I am pushing this thing, and I'm not pushing it left, right, left, right, left, right. I'm literally turning it. And what I do when I do that is I'm creating an alternating current, because the moment I get to the top, here I have my maximum current at this point, because that's when I'm at a maximum 90-degree angle. As I go more, I'm only cutting some. Here I'm cutting all of the magnetic fields at a 90-degree angle. At another point, I'm cutting less of the magnetic fields. That's why my current is decreasing. At the top here, I'm in line, going in the same direction as all the magnetic fields. That's why I have no current flowing. The moment I come down here, now I start cutting my magnetic fields, but I'm cutting down. At the other place, I was cutting up. And so when I'm cutting down, if I'm using my right-hand rule, okay, it's being pushed downwards, so my current is now flowing away from me. So at this point, my current was flowing towards me. Now my current is flowing away from me. So in the outside circuit, all of a sudden, my direction has changed. Okay, the direction of my current has changed, and that's now just in here. Okay, so what happens now is that if I were to plot over time my voltage, or it doesn't matter, I suppose voltage is the best thing to plot, and most common thing to plot. Let me just quickly see something. What I did here, what I drew here was, even though my current changed, again with the slip ring in the outside circuit, that doesn't have an effect, because even though my current changes, I again jump to the other side where the current now used to come from. So again, the slip ring causes the current in the outside. So the current in the loop is still alternating. It's now changing current. But because of my split ring, in the outside current, I'm still producing a direct current. My current is still. However, okay, my voltage still goes from a high volts, if that's now assuming that I start at this point. Okay, my voltage goes from a high volts down to 0. Okay, once I reach the top here. So it depends now how I measure my angle. Okay, if usually what we do is we start at this point. We say, okay, at this point, once I pass this point, I'm pushing up, so my current is coming towards me. Okay, so let's take this as 0 degrees. 0 degrees, that one is 90 degrees, that one is 180 degrees, 270 degrees, and this is 360 degrees. Okay, so if that's the case, let me just wipe that out. It's usually how we draw these graphs. If I start, then here at the bottom, I start at 0 degrees. But as I'm coming closer to where I will experience my maximum, cutting the maximum number of magnetic field lines. That would be at 90 degrees. So at 90 degrees, I will reach my maximum voltage. But then it will go down at 180 degrees, I will reach 0 voltage again. Now it just depends on what do I have here. I've got two options. Either I have split rings that look like this, which will jump the current each time, or I could have it could look like this. It's here's my circuit, here's my outside circuit, okay, with my load there. This one is connected here, and this one is connected here. Okay, so notice here, as this thing is turning, this is also just these rings. I can show you this picture that I have here. Okay, notice that this one is always, this side is always in contact with this side because of that circle. this is a bush, that one, that ring is always in contact with the same one. This one is always in contact with that bush. So if the current in this thing changes, since it's always in contact, the current in the outside circuit will change. Alternatively, we could then still have the split ring, okay, because the moment in the split ring, the moment that my current changes here at the top, I jump from going in this direction to going in this direction. Okay, so again, the split ring will mean that I am changing my alternating current. In this case, the split ring means I'm changing my alternating current into a direct current. And in motor's example, it was exactly the same. I had a direct current coming in and it was alternating the current in the loop. Okay, so if it's an alternating current, because I'm measuring my voltage here, notice the current in here is always alternating. If there's no slip ring, the current in the outside circuit must also be alternating. And then it means sometimes my current is in the positive direction, other times my current is in the negative direction. So for a complete turn, sometimes I will have a positive voltmeter reading and sometimes I will have a negative voltmeter reading. The highest reading when I'm cutting at this 90-degree angle. Make sense? Okay. But if I had my split rings in there, the moment it comes here, my current changes direction. So instead of going negative, it changes direction so that it keeps my current, my voltage positive. And so it will look like that. Okay. Good. Now, the value of this is obviously your maximum voltage that you can get. And your maximum voltage or your minimum voltage, they're just in opposite directions. But so we only work with maximum voltage, but maximum and minimum is the same, they're just in opposite directions. Okay? But the average voltage that you would get is called the RMS. I must be honest, I can't remember what that stands for. It's called the root mean square. Okay, that's a one way of finding the average value if the value follows the sine shape. Okay, so if it was a straight line, we would use average the way we usually use average. But once I follow a sine shape, then the average isn't anymore just taking half of the maximum. Okay, so that is, instead of taking half, we take the square root of that, which is less than half, more than half. Okay, so the root mean squared, that is kind of what what you can expect to get your voltage at. It will always change, but it's what you can bargain on. So, and that is just taking your maximum divided by the square root. Now I'll show you now why that's important. Okay, and by looking at the formulas. Now power is the amount of energy that you can convert into another energy every second. Okay, and the formula for power, when we're working with alternating current, okay, not just with alternating current, but with these fluctuating currents produced by a generator. So a generator doesn't give a consistent current, it gives this fluctuating between 0 and Vmax, 0 and Vmax, okay, is given by this formula. So the average power, so now you don't have a consistent power putting out, you have an average power that you put out. And notice that the average power that you put out is the volts times because remember, volts is how many joules I have per coulomb, and current is how many coulombs pass every second. So multiplying the joules per coulomb times the number of coulombs per second gives me the amount of joules I spend per second. Okay, let me show it mathematically. If volts is joules per coulomb and current is coulomb per second, then if I multiply these two values, the C's cancel out to give me joules per second. And that's exactly what power is. So if I want to know what is my average power that I spend, I will take the average voltage, which is now just the root mean square voltage, which is the average for that, times the average current. And again, the average current is calculated the exact same way. It's taking the maximum current that I get divided by the square root of 2. So we just need to do that because in this question, to go on with to answer these questions, the motor in the diagram is now changed to operate as a generator. So here they now say, okay, instead of this being a motor, it's now going to be a generator. Just looking at this, will this generator produce an AC current or a DC current? AC. The loop will always be AC. Okay. The question is, what is happening in here? DC. It's DC because of the split ring. This is AC the whole time, but the moment that split ring comes in, it changes. Whatever change happens in there just has no effect on the outside current. Or if it was a motor, the split ring will cause the direct current to change into an alternating current. So on what principles do generators operate? They change that principle is going from kinetic energy to electric energy. Okay. Draw a sketch graph of the potential difference versus time for this graph. So potential difference versus time for this thing is this graph. It just had to be a rough graph. Okay, but because it is a direct current, both of the loops are on top. Okay, and you got 2 marks, one for having the correct shape and one for having one at the top, another one at the top. Okay, the diagram below shows a dynamo attached to a wheel. Okay, when riding a bicycle, explain how a current is induced in a coil, and that's just where you get the Faraday's law. Is that when a magnetic field cuts a conductive material at a 90-degree angle, a current is induced in the conductor, and as the wheel is turning, it is rotating. So you can see here, it is rotating the magnet around a coil. A coil is just wound up wires. So obviously the more wires there are, the more electrons are being moved. Okay, so as the wheel is rotating, it is rotating the magnet to pass through the coil, inducing current. Okay. Now here's the question where I just want to show you, this is as difficult as it gets, really. It's not difficult at all. What is the peak voltage that the source can deliver? So let's just read the question. In the circuit we have an AC source. So there's my source is an AC source, and it's indicated, do you see that alternating current sine wave? Okay, the source delivers an alternating voltage at an audio frequency to the speaker. Okay, and there's just an additional resistor in, so that whatever voltage is being supplied is being corrected for the speaker. What is the peak voltage that the source can deliver? So here we have that our RMS is 20 volts, and did I do it correct now? If I look at my formula, RMS is the max divided by the square root of 2. So in other words, VRMS is V max divided by the square root of 2. Now they have given us, in this question, the root mean squared voltage. So they've given us 20 is equal to V max over square root 2. And so I just multiply both sides with the square root of 2. And this gives you something like 28,228 volts or something like that. Is it 28.28? Okay. So that's the maximum voltage that can be supplied. Okay. Calculate the average power delivered by the speaker. Okay, so remember what we said. Power, average power, is equal to the average RMS times the average volts times the average current. Okay, so first I need to go and find the average current. I've got average volts, but be careful now. Okay, if this thing counts 6 marks, it's definitely not finding just the average current. But let's find the average current. Okay, so average current is simply your average volts divided by, you can't have average resistance, you just do resistance. Okay, so in our case it's 20 divided by our average resistance here. Our resistance here is 9.4, and 12.6 gives me 22. Is it? Yes, 22 divided by 22. So that is 20 divided by 22 gives me 0.099 0.909. If there's nothing in front of the comma, I like to round to at least 3 decimal places. But this one I'm not going to round because it's not what they asked me. They didn't ask me for that, they asked me for power, so I'm only going to round to my final answer. Okay. The next thing, guys, just notice what's important here. They ask, calculate the average power delivered to the speaker. So I need to know what was the current that the speaker gets, and the speaker gets the whole current because he's in series. But the speaker doesn't get all of the energy. The energy is being reduced by this, so he doesn't get the whole 20 volts RMS. We must first go and calculate how much voltage does he get, and how much voltage does he get. Okay, he gets the whole current times his resistance. So 0.0909 what times his voltage is 12,6, and so the volts that he gets is 11.4545, etc., etc., etc. Again, that's not I'm not going to round because that's not my question. But now I know what is the average power that is used or expended at the speaker is this 11,4545, etc. times 0.90909, etc. So times it's roughly 1,04 watts. Okay, understand? So Again, it seems like most people thought it was easier than that. They just took RM, worked out total current and just substituted that. No, be very careful. They could say, what is the average power delivered by the source? And yes, then it is the source, the AC source is giving this much. But they're asking, what is it delivered to the speaker? Then it's about, well, how much energy is the speaker using per coulomb? And how many coulombs is he getting every second? In other words, the voltage and the current at that point. Okay. Alternating current is generated at power stations. Name 2 advantages of AC transmission over long distances. Well, there's various advantages. One advantage, for example, is we saw how easy it is to create alternating current, because if we go back here to my diagram here, notice that the 2 rings are in contact the whole time. Okay, so there's no jump of the current. Now, if you are generating high voltages and you're using a split ring, each time you jump that current, there's a spark, which means it damages your split rings. While here, there's no disconnection. So the split ring creates DC current, and DC current causes damages on those split rings. So it's more costly. So it's more cost effective to do alternating current. Alternating current also, if I have alternating current, it's easy to then change from kinetic energy, from electric energy to kinetic energy, because I already have my alternating current. So I don't need a split ring in my motor to turn my motor. Okay, so it's also easier to transform. So that's one thing, and it's and because you have alternating current, if you have DC current, high DC currents, your resistance, not your resistance, your wires have to be withstand much more power, because now you've got electrons going up, a whole lot of electrons going in the same direction the whole time, causing this thing to heat up a lot. I think that's the reason. Doesn't seem right, because but it's also over long distances. It's also you can carry higher currents, higher AC currents, alternating currents, than DC currents. So there's just a few, but there's a few more in the course as well. Cool. Any questions from you guys? So please do me a favor, go and practice past papers on these topics and get to questions that you don't know how to answer and ask me, so that I can address them, because I can really not find difficult questions. This one was now, this question, this number 6.1 is, but it's not difficult. Like, if you actually get, oh wait a minute, I just need to use the voltage for that. It's not complicated. It's just you have to keep your head on, so you read your question carefully. Okay, thanks guys. Sorry I went over a bit.